Hello everyone. Before we dive into today's topic, we want to take a moment to thank you for your support. Every like, comment, and subscription truly makes a difference and helps this channel grow. If you enjoy our content and don't want to miss upcoming videos, subscribe to the channel and ring the bell to receive all notifications. In the dark ocean of the primordial universe, when the first stars were just beginning to glimmer like scattered sparks in the void, something happened that still baffles astronomers today. In that young cosmos, barely a billion years after the Big Bang, a colossus emerged that shouldn't have existed. A grand, majestic spiral galaxy, its arms sharply defined, spiraling into the emptiness as if the universe had already mastered the art of cosmic harmony. Its name, Zhúlóng, evokes ancient mythology, a dragon of light capable of ushering in both day and night. A perfect symbol for a luminous structure born at the dawn of time. This galaxy is not just an anomaly. It poses a direct challenge to modern cosmological theories, which predicted a still chaotic universe dominated by violent collisions and shapeless clouds of gas and dust. The existence of such a complex and ordered structure at so early an epoch forces us to rethink the entire process of galaxy formation. How could a spiral galaxy, comparable in mass and size to our Milky Way, emerge so early in cosmic history? Zhúlóng spans over 60,000 light-years and possesses a stellar mass comparable to our galaxy. Yet what truly makes it extraordinary is its evolutionary state. The central core already appears quiescent, which means star formation there has ceased, while the outer arms blaze with vigorous starbirth. This pattern suggests an inside-out growth, where the inner region forms first and the outer parts continue to enrich themselves with new stars. Such behavior is observed in mature galaxies today, but finding it in such an ancient era is astonishing. But how did this galaxy become what it is? One plausible explanation lies in the remarkable efficiency with which Zhúlóng converted available gas into stars. While most primordial galaxies were still struggling through early stages of coalescence, Zhúlóng seems to have accelerated its development, quickly condensing baryonic matter into a stable system. It's as if, while the rest of the universe was walking, this galaxy was running. This rapid formation might be tied to the environment in which it was born. If Zhúlóng resided in a particularly dense region of the early cosmos, it could have benefited from a continuous inflow of cold gas, an essential ingredient for fueling star formation. But if it was instead an isolated object, its existence becomes even more mysterious, implying its evolution was not accelerated by interactions with other galaxies but driven by an internal process still not understood. The fact that a spiral galaxy managed to maintain such an ordered structure in an epoch rife with gravitational interactions also suggests another intriguing factor: a well-distributed dark matter halo. This invisible mass may have acted as a stabilizing frame, preventing destructive mergers from disrupting the symmetry of the spiral arms. In this sense, Zhúlóng also becomes an ideal laboratory to study the behavior of dark matter in the early universe. Another striking aspect is the precise geometry of its arms. Spiral galaxies generally form through prolonged dynamical processes, where density waves traverse the galactic disk, triggering star formation along spiral paths. These waves require a certain structural maturity and substantial mass. For Zhúlóng to exhibit these features so early indicates extraordinary gravitational stability, unusual for that cosmic period. What emerges from this discovery is a picture of the primordial universe far different from the chaotic, fragmented realm we often imagine. Zhúlóng shows us that the beauty and complexity of today's universe may not be the result of slow, steady evolution, but that in some cases, nature is capable of sudden, astonishing accelerations. A galaxy like this, with its elegance and precocity, opens new paths for scientific speculation. How many other such systems exist, hidden within folds of spacetime? The James Webb Space Telescope, with its ability to pierce cosmic fog and observe the universe as it was billions of years ago, provided the key to discovering this galaxy. But what now unfolds before astronomers is a new frontier. If Zhúlóng is real and confirmed, it likely isn't an exception but the first of a population of ancient spiral galaxies previously invisible to our instruments. In the second installment, we will continue this journey, delving into the implications that Zhúlóng's discovery has for our understanding of cosmic time, early gravitational structures, the role of dark matter, and the possibility that, from its origins, the universe held a hidden order we are only now beginning to sense. Yet, while science's gaze is fixed on Zhúlóng searching for answers, what this galaxy seems to offer us are even more questions. One of them: if the universe could sustain such complexity as early as 800 million years after the Big Bang, is cosmic evolution more varied, less linear, than we've always believed? And if some galaxies form with such rapid acceleration, what distinguishes those early bloomers from others that take billions of years to build? One fascinating theory suggests that there exist privileged regions in the fabric of the primordial universe. Areas where the initial matter density was slightly higher, where gas cooling and star formation could begin earlier and proceed faster. In these focal points, dark matter might have clumped into more symmetric and stable configurations, facilitating the formation of disks and spiral arms even in the cosmos' infancy. Zhúlóng may have been born in one of these gravitational oases, where conditions were perfectly calibrated to produce a galactic masterpiece. But it's not just Zhúlóng's origin that stimulates the mind. Its fate is also the subject of intense speculation. A galaxy so ordered, immersed in a still turbulence-filled universe, may not have preserved its shape for long. Perhaps it no longer exists, consumed by a merger with another galaxy or distorted by a cosmic collision. Or, in an even more evocative hypothesis, it might have evolved into one of the galaxies we observe today in the local universe, perhaps even as an ancestor of the Milky Way itself. Some theorize that phenomena like Zhúlóng are proof of a cosmic self-regulation principle, an unknown mechanism that guides the universe toward equilibrium even when conditions seem chaotic. This concept, still vague and speculative, would deeply impact our view of cosmogenesis. If the universe spontaneously gravitates toward ordered forms, even in its earliest phases, then the emergence of complex structures like spiral galaxies might not be an exception, but a hidden rule embedded in the fundamental laws of physics. Zhúlóng's case has also opened a new chapter in cosmological modeling. The simulations used so far did not anticipate the possibility of such structural organization so early. To accommodate this discovery, astrophysicists are now recalibrating simulation parameters, exploring whether higher spatial resolution, different treatments of stellar feedback, or new initial conditions can produce a system like this. The implications are profound. If we can replicate Zhúlóng in our models, we'll have proof that our theoretical tools are reliable. But if we can't, then something fundamental is eluding us. Even the future of astronomical observation will be profoundly influenced by this discovery. In the coming years, missions will focus increasingly on identifying and characterizing galaxies like Zhúlóng. Observatories like the Extremely Large Telescope, ELT, and the Square Kilometre Array, SKA, will be crucial for probing cold gas and dark matter in these primordial structures. It may become possible to measure internal dynamics, disk rotation, chemical composition, and perhaps even detect a central supermassive black hole, another element that, if present, would further complicate the theoretical picture. Finally, Zhúlóng's discovery forces us to reconsider another fundamental question. How unique is the Milky Way? Until now, our galaxy was seen as an example of an evolved structure, matured slowly over billions of years. But now we know that at least one twin existed much earlier. If Zhúlóng represents an evolutionary prototype, then perhaps our galaxy isn't the result of a slow, patient process, but the heir to an ancient dynasty of cosmic spirals that paved the way long before our sun was born. In this sense, gazing at Zhúlóng is somewhat like looking into our own past. Every arm that coils, every star that shines in that distant disk, might echo the history that led to our existence. Perhaps among the thousands of galaxies the James Webb will uncover in coming years, many more spirals like Zhúlóng will come to light. And with them, a new chapter of the grand narrative of the universe opens. One in which time is no longer a linear factor, but a flexible tapestry where complexity can emerge anywhere, even where we least expect it.